Hello, my friends. Today we are going to apply Lorentz force to a charged particles moving across a magnetic field. To begin with, let's recap what we have done in the last video. We have illustrated how the Lorentz force operates. In this case, with a given pair of magnets, we form a magnetic field between these two magnets. And if there is a conducting wire running across the magnetic field, in this case, in the x direction, then we will end up with a force. The force will pull the wire upward. And mathematically, Lorentz force is given by IL cross B. So in this case, we can substitute I itself is the conductive current. Conductive current is given by the time derivative of the charge. And if we substitute the time derivative of the charge into the original equation, then we will end up with a fresh equation. And with this equation, we can further develop another formula for Lorentz force. And this formula can be applied to a charged object moving across a magnetic field. So in this case, what I end up with is the interaction force is equal to Q, which is the charge of the charged particle. And then V cross B. V stands for the velocity, and B stands for the magnetic field. The total force is given by the electrostatic force plus the Lorentz force. And in this case, I have got the formula here. So today we are going to examine further how this charged particle behave in a magnetic field. Now, to begin with, right, let's clean up the board. And let's not forget what we have done last week in the last video. And our conclusion was the force is given by Q, V cos B. Now, we have already got this. Force is equal to Q, V cos B. And let's erase this diagram. And again, in this three-dimensional case, the z direction is in the vertical axis, x and y. Now, suppose you are now looking in the experimental setup from the right side. So this is your eye. Now, we are going to redraw the experimental setup in this space here. And the magnetic field is pointing towards the eye. So we can say that the magnetic field is pointing towards the So this is the magnetic field. And the charged particle is moving in the x direction from the perspective of the observer. The charged particle is moving from right to left. So if you have a charged particle, you are moving in here, moving along the x direction. So let's write down the direction on the vertical side is z, and the direction in the x direction, the axis in the x direction is here. We don't need this electric field. So this is the but because of the interaction between the magnetic field and the charge velocity, there is a force, and in this case, the force is pulling the charged object upwards. So in this case, the charged object Q is not going to move in the x direction only, but instead, as it moves towards to the left further, its height is going to be higher. So the actual movement locus will go this way, circular, and then bounce back. So the force that moves this charged particle here to in the vertical direction is in this case, in the beginning, the charge is moving upwards and leftward. And when the charge reach this area, then it will move further forward, but it is not in x direction only. Instead, because of the interaction of the Lorentz force, there is a pulling force pulling the charged particle towards the center of the circle formed by this locus. And as it goes further, there is a force pulling the charged particle towards the center. As a result, the locus of movement is going to be circular instead of being in a straight line. And eventually, the charged particle ends up leaving the magnetic field, and then it's going to be free of the interference of the magnetic field, and then it will just fly in a straight line. By Newton's law, the force pulling the particle towards the center is so-called the centrostatic force. centripetal force. It is given by mass times v squared over r over r. R is the radius of this circular locus. So you have R here, and R here should be the same. And according to the Roland force theory, this centripetal force is actually due to the Roland force. And in this case, in in the scalar form, we are going to have Q, V, B. And finally, we can conclude that M is equals to Q, B, R, QBR divided by V. The mass itself can be calculated from the radius of this circular locus, their magnetic field strength, and more importantly, the velocity of movement. So this is how the mass spectrometer works. Okay, thank you.